In this video, we're going to go from the percent composition to the empirical formula. So the opposite from what we did in the last video. And I really think the easiest way to do these is to just jump into an example right away and just go through the steps. So we're going to do that. Let's give you a title first though. So calculating the empirical formula from the percent composition. That's a long title, but that's our title. So our example, an unknown compound has a percent composition of 50.05% sulfur and 49.95% oxygen. And we're going to calculate the empirical formula of this compound. So we have two elements. We have the mass percent of each of those. And from that information, we're going to calculate our empirical formula. Remember, our empirical formula is our chemical formula, but in its most reduced form. So the first step, we'll do some steps here, is we want to convert the mass percent to mass, and we want that in grams. The easiest way to do this is to assume that you have a 100 gram sample total. So if I had 100 grams of this compound and 50.05% if it was sulfur, that means that I would have 50.05 grams of sulfur. If I had 100 grams total and 49.95% of that 100 grams, right, was oxygen, then I would have 49.95 grams of oxygen. You can assume whatever number you want. If you want to assume a 1 gram sample, then you have 0.5005 grams of sulfur and 0.4995 grams of oxygen. If you want to assume 50 grams, then you have 25.025 grams of sulfur, right? Half of that. However you want to do it is fine, the easiest way. And I always tell students they can assume whatever they want. No one's ever taken me up on it, so I assume you'll just do this too. But if we assume 100 gram sample, if we do that, then we simply just replace the percent sign with a G and you're good. So 50.05% sulfur would become 50.05 grams of sulfur, and then 49.95% oxygen would become 49.95 grams of oxygen. So if I have 100 grams total, and these are my percents, how many grams of each do I have? It's really as easy as just erasing that percent sign and putting a G in where it used to be. So I'm going to assume that 100 gram sample. Step 2 is we're going to convert grams to moles. And last week we learned how to do that. How do we convert between grams and moles? Hopefully you guys said molar mass. Remember, molar mass, my units are grams per mole, right? It's the number of grams in 1 mole of that substance. And anytime you have units where it's something over something, you use it to convert between those two things, right? So because my units are grams per mole, we use it to convert between grams and moles. So we're going to use our molar mass. We're always, incidentally, going to use molar mass to convert between those two things. If you have a periodic table and you know the mass, then you know the number of moles. And if you have a periodic table and you know the number of moles, you know the mass, because we can always convert between the two using the molar mass. You can go on and take like 6 more years of chemistry if you want. You're always going to convert between grams and moles using molar mass. We're never going to do it differently. So it's one of those conversions that you just need to know, right? If we have grams and we want to go to moles, we're going to use molar mass every single time. And that's the same substance. So moles of A, just A being something generic. So if I want to go from grams of water to moles of water, or grams of sulfur to moles of sulfur, we're always going to use that molar mass. Again, never any other way. So that's what we're going to do in this step. So I'm going to take my 50.05 grams of sulfur. I'm going to look on the periodic table to get my atomic mass, converting my units from atomic mass units to grams per mole. Because grams are on top, grams are going to have to go on the bottom. So 32.07 grams per mole. And I'm just going to, again, set them both up. I have 49.95 grams of oxygen. My molar mass for oxygen is 16 grams per mole. Again, because grams are on top, I'm going to have to divide by that molar mass to get those units to cancel, right? These grams are going to go away. So grabbing my calculator again, 50.05 divided by 32.07, I get 1.56, we need one more digit, 1 moles of sulfur. 49.95 divided by 16, 3.122 moles of oxygen. So our first step, we basically got rid of our percent sign and replaced it with a G for grams, right? We assumed a 100 gram sample, converted our mass percent to mass. In our second step, we converted mass to moles using our molar mass. Step 3 is we're going to set up mole ratios. And we're going to do that by taking the smaller number and dividing it into the larger number. We can do another example after this one where we have 3 different atoms, and there you're going to pick the smaller of the 3 and divide it into the other 2. So I always pick the smallest one and then divide it into everything else. So for this one, right, my moles of sulfur is smaller than my moles of oxygen, right? I have 1.561 versus 3.2. So I'm going to put the bigger one on top. So 3.122 moles of oxygen for every 1.561 moles of sulfur. So moles are going to cancel. And I'm going to just left with the number of oxygen atoms, essentially how much oxygen per sulfur do I have. Again, always put the bigger one on top, right? Take the smaller of the numbers and divide it into the others, meaning the smallest one goes on top. Sorry, the biggest one goes on top, the smallest one goes on the bottom. So the smallest into the others. We want our ratios to be greater than 1, not smaller than 1. Otherwise, it makes no sense. So this one actually comes out exactly to 2. It doesn't always come out exactly to 2, but this one did. So at this point, those ratios are going to become our subscripts. So step 4, the mole ratio. That's not possessive, sorry. Whatever, but geez. The mole ratios become the subscripts. And remember, the subscripts are representing the number of each type of atom that we have, and we can't have fractions of atoms, so we do need to round those to whole numbers. So we do need whole numbers. Sometimes it is okay to just round them. This one came out exact. If it didn't, and it's really close, you could round, but sometimes you're gonna have to multiply it by a factor, and we'll do an example like that also. So the mole ratios become the subscripts. We need whole numbers. Sometimes you can round, but often you will need to multiply by some factor or some multiple. And I will do an example like that. I just want you to have all the steps here. So we need whole numbers. Sometimes you can round. Honestly, most of the time you can't. You'll have to multiply it by some number to make it whole. So if it came out to be like 2.5, I can't just round that. I would actually have to multiply it by 2, and I would have 5 to 2 instead of 2.5 to 1. And again, we'll do an example. This one I don't have to, so I can just turn those into my subscripts. So my chemical formula, I have S, and you can put the subscript 1 if you want. You don't have to, and then O2. So this would be my empirical formula for a compound that had this percent composition. Another example for us, we'll do a couple more here. So we're going to again calculate the empirical formula of a compound that contains 84.1% carbon and 15.9% hydrogen by mass. So it's written a little bit differently. Instead of saying the percent composition is, I'm giving the percent and then telling you it's by mass, so we know that it's a percent composition. So I just wanted to word it a little bit differently, so if you come across problems that aren't worded exactly the way that I generally word them, it doesn't throw you. So same idea. I'm going to get rid of those percent signs, convert it to grams. I'm going to go from grams to moles using the molar mass. I'm going to set up mole ratios by taking the smaller of the numbers, dividing it into the larger number. And then I'm going to look at those and say, okay, I need them to be whole numbers. Can we round it, or do we need to multiply it by some sort of factor? So our first step, I know that if I have 84.1% and I assume 100 gram sample, I have 84.1 grams of carbon. I know that if I have 100 gram sample and 15.9% of it is hydrogen, I have 15.9 grams of hydrogen. Step 2, we're going to convert to moles by dividing through by the molar mass. So again, these are just coming from our periodic table. I do need to divide, right? Because grams are on top. I need them to cancel, and the only way to do that is to have them on the bottom. So my grams are going to go away, and we're going to be left with moles. So grabbing my calculator, 84.1 divided by 12.01. I end up with 7.00 moles of carbon. 15.9 divided by 1.01. I have 15.7 moles of hydrogen. So that was my first two steps. We're then going to set up mole ratios. My moles of carbon is the smaller number, so that's going to be divided into my moles of hydrogen. And when I work that out, I got 2.24 hydrogen, moles are gone now, for every 1 carbon. So this is one of the ones where I just can't round it. It needs to be really close. Like if it was 2.0 something or 1.9 something, I could round it. But 2.24, I can't round this. So what I'm going to do is I need to multiply it by something. And then we also need to remember that we can't change our ratio, right? If I was to just multiply the top number and not the bottom number, now I've changed my ratio. You change the ratio, you've changed your number of moles, and then you've changed your original mass percent, right? It's not the same anymore. So whatever I do to the top number, I also have to do to the bottom number. I don't want to change my ratio. I just want to multiply it by something to make it a whole number. So I know if it's 0.24, that's really close to 0.25. So if I multiply by 4, I'm going to get something that's close enough to a whole number to be able to round it. And again, you need to multiply both of them. I don't want to change my ratio. So I want to multiply by 1, essentially, right? 4 over 4 is 1. So whatever you do to the top, you have to do to the bottom also. Otherwise, you're going to get the incorrect answer. So when I do that, I end up with 8.96. I'm just going to write it all out, and then you'll see how we can round it to 4 carbon, right? Do it on both the top and the bottom. So that is going to give me 9 hydrogen for every 4 carbon. So then when I write my empirical formula, C4H9. We are going to add one more part to this, and that's to calculate our molecular formula. So what is the molecular formula? Of this compound if the molar mass of the molecule is 114.2 grams per mole. Remember, our molecular mass, our molecular formula is not always reduced. So what we want to do is we want to scale this up, right? We want to find out, okay, do I need to double those subscripts, triple those subscripts? How do we scale that up to my molecular formula? Remember, empirical is always the smallest whole number ratio. My molecular formula isn't necessarily the smallest whole number ratio. Remember, sometimes they can be the same. So how we're going to do that is we're actually going to figure out a multiple. So we're going to take the molar mass of the molecule, which has to be given as part of the problem, because we wouldn't know that. We don't know what the chemical formula or what the molecular formula is. Without the molecular formula, we can't calculate the molar mass of the molecule. So that would have to be given to us. So we're going to take that number, which is in my problem right here, and we're going to divide it by the molar mass of the empirical formula, which I know it's kind of weird wording, but I'm going to take the C4H9 and figure out what the molar mass of that is. Maybe the word 4 is better than of. Molar mass 4, the empirical formula, and then I guess to be consistent, we could say molar mass for the molecular formula. And then that's going to give us a multiple. Once we get that multiple, we'll multiply the subscripts in my empirical formula by it to scale it back up. So the molar mass, I'm getting tongue-tied. The molar mass of the molecular formula is given to us. We do need to calculate the molar mass of my empirical formula. So we just solved for it and said we have 4 carbons. And we have 9 hydrogen. Again, those values are just coming from our periodic table. Hopefully by now you guys are getting pretty comfortable with calculating molar masses. And then we add that together. So I'm grabbing my calculator that we can probably add 2 numbers without it. and I got 57.13 grams per mole. So we're then going to take the molar mass of my molecule, which is given to us, so 114.2 grams per mole. I'm going to divide that by the molar mass of my empirical formula, which we just calculated. And when I divide that out, I get 1.9989, which is close enough to round to 2. So my multiple is 2. So what that means, I'm just rewriting my empirical formula here, is I am going to multiply both of those coefficients, or sorry, both of those subscripts by 2. So C8, H18 is my molecular formula. If the coefficient would have come out to be, or if the multiple, sorry, would have come out to be 1, then my empirical formula is my molecular formula, right? That's how it would come out with water. So take the molar mass for your molecule, or molecular formula, molar mass for the empirical formula, divide them, get our multiple. Once you do that, multiply your subscripts by that multiple to scale it back up. So let's go through one more example. So again, what is the empirical formula? Of a compound that is 57.54% carbon, 3.45% hydrogen, and 39.01% fluorine by mass. So same steps. I'm going to convert my mass percent to grams by assuming a 100 gram sample and just replacing the percent sign with a G. I'm going to then convert from grams to moles using the molar mass, and then we'll set up our mole ratios. This time we have 3 different atoms, so we'll pick the one that has the smallest number of moles and divide it into the other 2. Then we'll look to see if we can round it or if we have to scale it up by multiplying it by some number. So I have 57.54 grams of carbon, right? I'm going to assume that 100 gram sample. I'm going to leave a little space because I'm just going to convert to moles right under it. 3.45 grams of hydrogen and 39.01 grams of fluorine. Divide by the molar mass to convert between grams and moles. Again, these numbers are just coming from our periodic table. When we do that, our grams are going to cancel, right? If it was on top, we put it on the bottom, so we're dividing. So I'm grabbing my calculator and we'll work these out. Hopefully you guys are also typing these into your calculator right now. Moles of fluorine. So I got 4.791 moles of carbon, 3.42 moles of hydrogen, and then 2.053 moles of fluorine. So this is where we're going to pick the smaller of the numbers. So 2.053 is smaller than my other numbers of moles. And then that's going to get divided into the other 2. So 4.791 moles of carbon for every 2.053 moles of fluorine, and then 3.42 moles of hydrogen for every 2.053 moles of fluorine. So working that out, I'm ending up with 2.334 carbon for every 1 fluorine. And 1.66 hydrogen for every 1 fluorine. So these ones we're gonna have to multiply by some number also. We can't just round them. Again, they would have to be like really close, like 0.9 or 0.0. 0.1 if you're in lab, since these aren't lab values, right? I'm actually making them up. They will be close enough that it should hopefully be obvious when you can round and when you can't. So in this case, you can't. So what do I need to multiply it by to make it a whole number? So if it was like close to 0.25, I would multiply it by 4. If it was close to 0.5, I would multiply it by 2. If it's close to 0.33, we're going to multiply it by 3. Again, don't forget that whatever you do to one, you have to do to both. So not just both numbers in one ratio, but all the numbers. I don't want to change the relationship between these. I just want to scale it. So by multiplying both by 3/3, I'm essentially just multiplying it by 1, which means I'm not changing anything. I'm just scaling it up. So be careful. So for this one, I got 4 points. I guess it rounds right up when I do sig figs here. 5 hydrogen. We are going to have to round into whole numbers, so I'm just doing that right now. So what I got was 4.9975. If I was to round that to the 3 significant digits, it would round to 5.00. And when I turn them into my subscripts, I would drop that 0.00. So I'm just doing it right away. 2.334 times 3 is giving me 7.002, so 7 carbon for every 1 fluorine. Oh, did you guys see what I just did? I like harp forever about making sure you multiply them by them both, and I didn't do that. I wrote it, right? I put a 3 there, but then I didn't do it. So 5 hydrogen for every 3 fluorine, right? 1 fluorine multiplied by 3 gives me 3 fluorine. And then 7 carbon for every 3 fluorine. If I had different numbers of fluorine on the bottom, then the ratios wouldn't make sense neither. Now I'm just going to turn those into my subscripts. So I have C7, I have 5 hydrogen, and then I have 3 fluorine. So that would be my empirical formula for this one.